Hello and welcome back to App for You. In this particular video we will basically discuss about Master's theorem for subtract and conquer recurrences, right? So I have already made a video on Master's theorem for divide and conquer recurrence problem, right, wherein we had the expression of the form t of n is equal to a t n by b plus theta n power k log of b n, right? So this particular expression was basically for Master's theorem for the problems having divide and conquer recurrences. And clearly, since we were dividing the problem n into sub problems, so it was needed for b to be greater than 1, because if b is equal to 1, right, if b is equal to 1, then you are not going to divide it, right, because the problem remains the same, the size of the problem remains the same. But we want to divide the problem into more sub problems, so that is why b should be greater than 1. We had already discussed this criteria, isn't it, for the divide and conquer problem. But now in this particular video we are going to discuss about Master's theorem for subtract and conquer recurrences. Master's theorem for subtract and conquer recurrences. How do we do this, and what is it all about? Let's discuss. So basically what happens is, we may have a function of the form for some positive values of n having the property such that t of n is equal to c if the value of n is less than equal to 1. Okay, but if n is greater than 1, okay, if n is greater than 1, then the tn, that is the recurrence relation, takes the form tn equal to atn minus b plus f of n. Alright, getting the point? So tn equal to atn minus b plus f of n means some function of n, okay, for n is greater than 1. Okay, so let tn be a function defined on positive n and having the property this. Okay, then what happens is, for some constants c and some value a greater than 0, some value b greater than or equal to 0, and some value k greater than or equal to 0, these are the essential conditions. Okay, and function fn, okay, if fn is in order n power k, means the function we have already discussed, right, that fn is some function of n, and we find that this function n is of the form order n power k. Okay, then in that case the complexity of this can be calculated as per this condition. Getting the point? Things are very easy, just you have to decode it. So what it said is, let tn be a function defined on positive n, okay, that has the property. What is the property? This is the property that tn will take the value c, some constant, if n is less than equal to 1, and for n greater than 1 it takes the form of this tn equal to atn minus b plus fn. What is fn? Fn is in order n power k, some function of n which is in order n power k. Okay, and the values of the variables here a, b, k should be of this format, that is k should be greater than equal to 0, b should be greater than equal to 0, a should be greater than 0, and some constant c should be there. In that case the complexity can be directly achieved as per this condition. What is the condition? Now once you found out these things, once you found out these variables, okay, then if you see that the value of a is less than 1, okay, if the value of a is less than 1, then the time complexity will be of order n power k. You already know what is the value of k because you have already typed there. But if the value of a is equal to 1, the complexity will be of order n power k plus 1. Getting the point? But if the value of a is greater than 1, the complexity will be of order n power k a power n by b. Fine. So there are three conditions, you all are depending on the value of a, whatever value of a you have seen from the above expression, right? Because I've already said you, if n is less than equal to 1, you will have some constant value, but if n is greater than 1, you will have some expression of the form atn minus b plus fn. Now if you compare your recurrence relation with this format, you will get the values of a, you will get the value of b, and also since we know that fn should be of the form n power k, from there you can get the value of k also. Now having said that, you will just now find the values of a. So if a is less than 1, the complexity is order n power k. If the value of a is equal to 1, the complexity will be of order n power k plus 1, right? And if a is greater than 1, then the complexity is of order n power k a power n by b. This will become more clear with the help of the example. Let us quickly jump into the example. So here you can clearly see we have a function, okay, and it receives the value of n, some value of n, and then if n is equal to 1, it will directly return from here only. Okay, but if it is not equal to 1, if there are some values, suppose n equal to 10 or 20, anything, then it enters this for loop, because for I is equal to 1, I less than equal to n, I plus plus. How many times will it get executed? From 1 to n, from 1 to n and incrementing 1 at each step. So it is executing order n times, okay, the outer for loop. And you have one more for loop inside, which is executing from 1 j equal to 1 till j less than equal to n and 1 at each step. So this is also getting executed n times. Okay, we have already discussed this in the previous video. So what is the overall complexity of this for loop? Okay, the overall complexity of this for loop is n square, isn't it? Right, order of n square. Fine. Now again, once you complete the execution of this for loop, again you can see there is a recursive call to the function n minus 3. Okay, initially the size of the problem was n, you perform some operation, and then again you are doing a recursive call on the function n minus 3. Now you know that in case of such recursive calls and recursion used in the function, we can have a recurrence relation. So the recurrence relation will be of form Tn is equal to Tn minus 3 plus some constant into n square. Okay, n square I am taking here because of this for loop. This for loop here is taking order n square and just multiplying it by some constant c. Okay, so this is your recurrence relation of this particular problem, right? You can clearly see Cn square is derived by the complexity of this for loop used here, and then we are calling a function Tn minus 3, right? The function size is reduced by 3, Tn minus 3. Now this is your problem. What is the recurrence problem? Now you can clearly see from the above problem we derived this recurrence relation that Tn is going to be a form Tn minus 3 plus c into n square. Okay, how do you find the complexity of this particular recurrence relation? We can see just now we discussed Master's theorem for subtract and conquer recurrence relations. What did it say? It basically said that if Tn takes the form Atn minus b, let me write here, Tn equal to Atn minus b plus some fn. And what is fn? Fn is nothing but order of n power k. Fine. And a is greater than 0, b greater than equal to 0. So you can see a is 1 here, isn't it? If you compare these two recurrence relations, you will find that a is equal to 1. Fine. B is 3. So obviously b is greater than equal to 0. Satisfied. K is 2 and k is also greater than equal to 0. So all the conditions are satisfied. So now basically what will be the complexity of the code? The complexity of the code will depend on the value of a here. What is the value of a we have? We have a is equal to 1, right? So let me write here. On comparing, we found that a is equal to 1, b is equal to 3, k is equal to 2. All the conditions, all the essential conditions here are satisfied, right? All these conditions are satisfied. Now we know that if a is equal to 1, the time complexity will be order n power k plus 1, right? So we have a equal to 1, so the complexity will be of order n power k plus 1, which is equal to order n power, what is the value of k we found? T, 2, isn't it? 2 plus 1, which is equal to order of n cube. Getting the point? So this is how we can use the subtract and conquer problem. Okay, the subtract and conquer recurrence relation. Okay, how we can apply Master's theorem in such problems that has subtract and conquer recurrences. So this was the definition that we discussed. The formula is in front of you, and the example, a very good example of this problem, of the application of this particular principle is here. So I hope you understood this. Thanks for watching, and please like and subscribe.